Hello everybody. Yesterday I decided that I will be making a new video every day, and today I just want to go through my Facebook posts. First I noted that it was snowing, that was quite nice, and then I looked at my predictions of the masses of the muon and the tauon from 2016. And back then I had two approaches, and basically in space particle dualism theory, every particle has its own quantum of space, or you could simply say that every particle is a quantum of space. It's a complex two-sphere with a radius that is proportional to its mass. And so it's a bit similar to a black hole, and you could imagine having we can have merging black holes, so why not have merging elementary particles? And of course they have to reach critical energy for that. It's the energy where the elementary space becomes, the space atom becomes larger than the wavelength of the particle. So I will spare you the details of the exact calculation. I'm currently reviewing two very old chapters. This is from, I initially wrote about this in 2005. This is a bit thinking about how you would get, how you could get rest mass particles from photons. This start out from a general relativity perspective, where you have where particles can be black holes. Well, that's not possible in space parallelism theory, because photons don't have gravity, they don't have a Schwarzschild radius. So anyway, I don't want to make this video too long, so I'm going to only look at, here I'm reviewing, I will look only at this chapter here. I'm reviewing, overhauling this chapter here, but this is a very old chapter, and I underestimated it a bit. I always thought this chapter is sort of like the weakest point in my book, the weakest chapter, but actually it is not. It is actually not bad. So here I try to predict the mass of the muon and the tauon, and I actually got pretty close, but back then I didn't write down how many percent of the actual value I got. And basically if it's more than 10%, then you can say it's at least in the right order of magnitude. Actually here we got to 86%, and for the tauon 54%. So this is assuming that two electrons merge, and that's the mass you get, and then you have 3 electrons, and then you get the tauon mass. And then the other approach, and for charge conservation reasons, you have a positron pop up nearby, and I think that's the right approach. But the other approach, which I pursued here, and I seem to have favored it back then for some reason, is to actually have 2 electrons and a positron merge together, like becoming one, like 3 black holes merging together. And that's quite unrealistic, and I mean they would annihilate each other, and it's quite problematic. And also when you calculate the percentages, which I did in my Facebook post, it's a pretty poor result. It's 49% and 90% instead of, when we use the more reasonable approach, it's 86% and 54%. So so now what could explain these discrepancies? Back in 2016 I thought maybe it's some running of coupling issue that can explain it. But when we look at the Koide formula, here, Koide formula, you can see that this is the Koide formula. It's very orderly, and they are very well distributed. The masses of those three particles, they fulfill this equation here. And so what could round them up in a manner of speaking to give this wonderful equation here? And my suspicion is, since quite a while, is that we don't only have flavor mixing with the different neutrinos, but also with the electron, muon, and tauon. So the mass of the electron must have some contributions, some virtual contributions from those other two flavors, from the muon and the tauon. And so if every one of them is a mix of all the three, then that would explain why the Koide formula can be true. And it's true with very high precision. So yeah, that's one thing. And then I also thought a little bit about chromogravity, like my chromogravity spacecraft idea. I haven't explained this on this channel, but basically, if gravity depends on the number of baryons or quarks, and you increase, and not on mass, but then you increase the mass by means of mass inflation by using particle accelerators, then you can manipulate gravity, and it goes according to this equation here. The gravitational acceleration here, you have the mass here, so it's balanced out normally by this blackboard bold y, which is the number of quarks. But here, when you increase the mass without increasing the number of quarks, then the balance is off. And so if you double the mass and you don't do anything here, then basically g is reduced to half. But the interesting aspect is that you wouldn't be able to measure it on a scale, because a scale is basically measuring weight, and that's mass multiplied by acceleration. And so but you could measure it on a balance. So my father used to have a balance, and it seemed quite impractical, but it's much more precise. Because a scale, if you take it to a high mountain, it will show something else than near the sea. Yeah, so that's an interesting aspect. So my spaceship would get much heavier, but it wouldn't show up on a scale, only on a balance. Yeah. Sorry, I didn't intend to click on that. Okay, by the way, this background here, this is my supernova survey, where I proved that the intergalactic distances provided by my theory are accurate. Yeah, so here SPD, here it matches up, and GR doesn't match up. You see this aligns, and this is the expectation for GR, but this crosses over here after 1, so here, and here it's 2, the 2 blocks here. So anyway, but that's a topic for another time. So that's all for today. Have a nice day, and I will go to sleep now. Bye bye.